In this lesson, we will review how to determine when sequences and series converge or diverge, and when possible, we will find the actual sum of a series. So first, the difference between a sequence and a series. So a sequence is just a list of numbers. It's not adding those numbers up. So to determine whether a sequence converges or diverges, you just take the limit as n goes to infinity of the terms. And then for this particular example, you can multiply the numerator and denominator by 1 over e to the n, or equivalently divide the numerator and denominator by e to the n. And you have the limit as n goes to infinity of 5 minus 1 over e to the n over 2 over e to the n plus 3. And both 1 over e to the n and 2 over e to the n go to 0. So this limit is 5/3. Now to find the limit as n goes to infinity of ln n over root n, you can use L'Hopital's rule, but technically to do that you have to have a function. So this n implies that you only have integers, so you have to use f of x equals ln x over root x. So the limit as x goes to infinity of ln x over root x. Now as x goes to infinity, ln of x goes to infinity, and so does root x, so this is an infinity over infinity form. So let me know you applied L'Hopital's rule. We've got the limit as x goes to infinity, 1 over x over 1/2 x to the negative 1/2. Which will simplify to 1 over x multiplied by 2 root x over 1, which is the same thing as the limit as x goes to infinity, 2 over root x, which is 0. Now, next we discussed series, and the first example of a series that we had was a geometric series, which we actually could compute the sum of. And this series converges if r's absolute value is less than 1. So before you even start to try to find a sum, you should check and see if that r is less than 1. And the other thing is this formula is what it is because this series begins at 0. If your series doesn't begin at 0, you're going to have to change the indexing set so that it does, and you can apply the formula. Alright, here we have the sum from n equals 0 to infinity, 5 times e over 3 to the n. So first of all, it does start at 0, so if we are going to determine this converges, we're good to go with the formula. But we just have to figure out, first of all, is e over 3 less than 1? And since e is approximately 2.71, that means that e over 3 is certainly less than 1. So this thing does converge. And it converges to 5 over 1 minus e over 3. To simplify that, we could multiply the numerator and denominator both by 3. And that will give us 15 over 3 minus e. Now next we have negative 3 to the n minus 1 and 2 to the 3n. And also our series begins at 1, so we're going to have to deal with that eventually. But first let's start by doing this. That negative 3 to the n minus 1 is the same thing as negative 3 to the n, and the negative 3 to the negative first. And then 2 to the 3n is the same thing as 2 to the third to the n, so that's 8 to the n. Negative 3 to the negative first is negative 1/3. So we'll have negative 1/3 times negative 3/8 to the nth power. Now we know now that this will converge because 3/8, the absolute value of negative 3/8 is less than 1. But now we have to change the indexing set. So we change this to a sum from n equals 0 to infinity. Negative 1/3. and the negative 3/8 will be raised to the n plus first power. And you can just check and see that they're the same. When you plug in 1 in the black one, you have negative 1/3 times negative 3/8 to the first, plugging into negative 1/3, negative 3 squared. The blue one, same thing, negative 1/3, negative 3/8 to the 0 plus 1, which is 1. And now to simplify that, so we can actually apply our formula, this is the same thing as the sum from n equals 0 to infinity, negative 1/3, negative 3/8 times negative 3/8 to the n. So that will be, my a factor will actually be 1/8. So I have 1/8 divided by 1 minus negative 3/8. And if I multiply the numerator and denominator both by 8, I get 1 over 8 plus 3, which is 1 over 11. The other series that we could also find sums of are telescoping series. And how we do that is we find the expression for the partial sum s sub n, and this is equal to the limit as n goes to infinity of that partial sum s sub n. So s sub n, first we plug in 3, we'll have 1 over 1 minus 1/3. Then we plug in 4, we'll have 1/2 minus 1/4. And then 5 plus 1/3 minus 1/5. And then we'll plug in 6 just to see what's happening. We will have 1/4 minus 1/6, etc. Now the last term we will have would be 1 over n minus 2 minus 1 over n. And one prior to that will be 1 over n minus 1 minus 1 over n minus 3. Now notice nothing cancels this 1, nothing cancels this 1/2, but that 1/3 cancels with that 1/3, this 1/4 cancels with that 1/4. So the first two terms don't cancel, and also the last two terms don't cancel. So s sub n is equal to 1 plus 1/2 plus 1 over n minus 3 plus 1 over n minus 2. And if I take a limit of this expression as n goes to infinity, I get 1 plus 3 over 2, or 1 plus 1/2, which is 3 over 2. And telescoping sums can also involve tricky things like logs and inverse tans. So let's see how this one works. So once again, this will equal the limit as n goes to infinity of the nth partial sum. So when we plug in 1, we have inverse tangent of 2 minus inverse tangent of 1. When we plug in 2, we have inverse tangent of 3 minus inverse tangent of 2. I'll just plug in one more. We plug in the next one, plug in 3. We'll have inverse tangent of 4 minus inverse tangent of 3. And the last term we will have will be tan inverse of n plus 1 minus tan inverse of n. And just one previous term will be tan inverse of n minus 1, and then minus tan inverse n. Okay, what you can see is this tan inverse 2 cancels with that one, the tan inverse 3's cancel, the inverse tangents of n minus 1, the n's cancel, the n minus 1 will cancel with the previous term. So what we have for Sn is negative tan inverse of 1 plus tan inverse of n plus 1. And the limit as n goes to infinity of s sub n will equal, well, first the value of inverse tangent of 1, which is pi quarters, so negative pi quarters. And then as n goes to infinity, inverse tangent looks like this, and it is bounded by pi over 2, so that limit is pi over 2. And negative pi quarters plus pi over 2 is pi quarters. So this sums to pi quarters. Explain why the following series diverge. So for this example, if we check the limit as n goes to infinity of the terms, this is equal to 1/3. And the test for divergence says that the limit as n goes to infinities of the terms has to be 0. And if that's not the case, the series will diverge. So since this is not equal to 0, this series diverges by the test for divergence. Here we have pi over 3 to the n. Well, since pi is about equal to 3.14, that tells us that pi over 3 is greater than 1. So this is a divergent geometric series. Because r is greater than 1. And the next question, true or false? If you have the sum from n equals 1 to infinity of a sub n, and the limit of the terms goes to 0, then the series converges. Is that true or false? Does every series whose terms go to 0, does every series like that converge? And this is actually false. The best example would be the harmonic series, n equals 1 to infinity, 1 over n. In this example, 1 over n goes to 0 as n goes to infinity, but this series diverges. So what you have is that if the limit as n goes to infinity of a sub n is not equal to 0, then you know that you diverge. But if the limit equals 0, it could go either way. So you can use that test for divergence to check and see if it diverges, but you cannot conclude convergence from it. Now the next test we had was the integral test. And in order to apply the integral test, you had to have a function, f of x. So we're going to use f of x equals 1 over x root ln x. And the conditions were f must be continuous, positive, and decreasing. In this case, on the interval from 2 to infinity. So I will give you some way to show that, say like graphically, or give you a derivative, but those are the conditions that must be met. And if those conditions are met, you can find the value of the integral from 2 to infinity, 1 over x root ln x dx. And if this integral converges, then the series converges. And if this integral diverges, then the series diverges. So this is equal to a limit as b goes to infinity, 2 to b, 1 over x root ln of x. If you have to do a u sub on your own, you would u sub for ln x. And when you do that u substitution, you get 2 root ln x, evaluated from 2 to b. So this is the limit as b goes to infinity, 2 root ln of b minus 2 root ln of 2, which is infinite. And thus the series diverges. One nice consequence of the integral test is it also gave us a means of estimating the error that we have if we estimate an infinite series with a finite number of things. So what that said, as long as you have something for which the integral test applies, the error is less than or equal to the integral from n plus 1 to infinity of your function. So if I wanted to estimate 1 over n cubed from 1 to infinity with the sum from n equals 1 to 5, the error is less than or equal to the integral from 6 to infinity of 1 over x cubed dx, which can be found by taking a limit as n, well, say b, goes to infinity. Integral from 6 to b, x to the negative 3 dx. It's x to the negative 2 over negative 2, evaluated from 6 to b, which will be the limit as b goes to infinity, negative 1 over 2b squared plus 1 over 2 times 6 squared, which will be 0 plus 1 over 72. So the error is less than or equal to 1/72. That doesn't mean that the error, like that, this is the absolute worst case scenario. So the error could actually be smaller than this, but this is the worst it's going to be. Now the next tests that we had were the comparison tests. And with the comparison tests, you could either directly compare your series to a known series, or you can use the limit comparison test. So for the first example, this series is awfully like 1 over 3 to the n. And notice that this is true. N plus 3 to the n is bigger than 3 to the n because we have positive n's. So 1 over n plus 3 to the n is less than 1 over 3 to the n. And you know that the sum from n equals 1 to infinity of 1 over 3 to the n converges, because it's a geometric series with r equal 1/3, which is less than 1. And because your series' terms are smaller than that, converges by direct comparison. So if you have a smaller series, if you have a series that is smaller than a known, with terms smaller than a known series that converges, then your series must also converge. Now the opposite is true with divergence. If you have a series you know is divergent and another one whose terms are larger, then the larger termed series must also diverge. This does also rely on the fact that your terms are actually positive, so the fact that this is bigger than 0 is actually somewhat important. Alright, here. Well, I should have changed something slightly. This shouldn't say n equals 1, it should say something like n equals 2. Otherwise I have division by 0 my first term. But anyhow, so notice here that n to the 4th minus 1, that's less than n to the 4th. So 1 over n to the 4th minus 1 is greater than 1 over n to the 4th. And because n is positive, we have n cubed over n to the 4th minus 1 is greater than n cubed over n to the 4th, which is 1 over n. And since the sum from n equals 2 to infinity of 1 over n diverges, the sum from n equals 2 to infinity n cubed over n to the 4th minus 1 also diverges. Now, if direct comparison is hard to establish, you can use the limit comparison test. And with this test, you choose two series, an and bn, where an is, some of an's is like the one you know, so I'm going to let an equal n squared plus 1 over n cubed plus 1. And I'll let bn equal 1 over n. I kind of get that by ignoring all the plus 1s and canceling stuff. And when I find the limit, as n goes to infinity of an over bn, if this limit is a finite number, then both series do the same thing. So I have the limit as n goes to infinity of n squared plus 1 over n cubed plus 1. Now dividing by bn is the same thing as multiplying by n over 1, which gives us the limit as n goes to infinity, n cubed plus n over n cubed plus 1, and that limit is 1. So thus your series diverges by the limit comparison test. And let's try the same thing here with n plus 4 to the n over n plus 6 to the n. So if I ignore those n's, this is an awful lot like 4 over 6 to the n. So I'm going to have a to the n equal n plus 4 to the n over n plus 6 to the n, and b sub n equal 4 to the n over 6 to the n. And we'll find the limit as n goes to infinity of an over bn. So that will be n plus 4 to the n over n plus 6 to the n multiplied by 6 to the n over 4 to the n, which gives us a limit as n goes to infinity of n 6 to the n plus 24 to the n over n 4 to the n plus 24 to the n. And from here, I'm going to multiply by 1 over 24 to the n. And that gives us the limit as n goes to infinity of n over 4 to the n plus 1 over n over 6 to the n plus 1. And technically, you could use L'Hopital's rule, assuming you change your n's to x's, to prove that both this limit and that limit are going to be 0 individually. So this limit will equal 1. And so because the sum of the b sub n's is convergent, your series is convergent. And the next test we had was the alternating series test, and this is the first test that we encountered that allowed us to deal with series that had some negative terms. And this one specifically deals with series that alternate. And the alternating series test says that your series will converge if the limit of your terms is 0 and the terms are decreasing. So first let's establish that the limit as n goes to infinity of 1 over n ln of n, well, that's definitely 0 because you have 1 over something that's growing. So one condition is met. And the second condition, it is true that 1 over n plus 1 times ln of n plus 1, that is definitely bigger than or equal to 1 over n ln of n. So your terms are also decreasing. And that's true because ln of n is an increasing function. So by the AST, the series converges. Now here we have negative 1 to the n times n over n plus 2, and the limit as n goes to infinity of n over n plus 2 is equal to 1, which is not equal to 0. So thus the series diverges. And the alternating series test also gave us a great way to estimate error. So what this said is that the error was less than or equal to the next term that you left off. So for this particular example, the absolute value of my error, since I summed for the first n terms, is less than or equal to the absolute value of the 11th term, which is 1 over 11 to the 3 halves, which you could get a decimal for, but that's the same thing as 1 over 11 square root of 11. And the other thing we discussed here was the difference between conditional convergence and absolute convergence. So a series is conditionally convergent if the series converges but its absolute value does not. A great example is the sum from n equals 1 to infinity, negative 1 to the n over n. This converges by the AST, but its absolute value does not. It's the harmonic series. An example of an absolutely convergent series would be something like n equals 1 to infinity, negative 1 to the n over, say, n squared. This also converges by the AST, and its absolute value, which is 1 over n squared, converges because it's a convergent p-series. Now, next, we also learned that absolute convergence implies convergence. So this might let you handle series for which that is not an alternating series. Like, for example, here, cosine of 3n is going to not necessarily flip-flop positive negative. It's going to have some positive terms, some negative terms, not necessarily in a really easy pattern. But it is bounded, so what you can notice is that the absolute value of cosine of 3n over 1 plus 1.2 to the n, that's less than or equal to 1 over 1 plus 1.2 to the n, because cosine is bounded between negative 1 and 1, which is less than 1 over 1.2 to the n. And notice that, well, this is the same thing as 1 over 1.2 to the n, and 1 over 1.2 is less than 1. So this is we have that the sum from n equals 1 to infinity, 1 over 1.2 to the n is convergent because it's a geometric series. And of course, 1 over 1.2 can be simplified to 5/6, but anyhow. So that's a geometric series, and by direct comparison, you have that the sum from n equals 1 to infinity of cosine 3n over 1 plus 1.2 to the n converges. And so thus the series is absolutely convergent, and therefore convergent. Next came everybody's favorite tests, the ratio test and the root test. Both of these tests prove absolute convergence. Now, obviously I'm going to make some problems where you cannot use these tests all the time, so sometimes these tests fail and you cannot use them. Just be aware of when that is. When you get that the limit is 1 in either case, you have to apply a different test. So for this one, because both the numerator and denominator are raised to the nth power, I'm going to apply the root test. So for that, we find the limit as n goes to infinity of the nth root of the absolute value of the terms. So the nth root of n to the 2n over 1 plus 2n squared to the n. And I don't need the absolute value there because these terms are all positive. So we have the limit as n goes to infinity of n squared over 1 plus 2n squared, and that limit is 1/2, which is less than 1. So by the root test, the series converges absolutely. Next, let's do a ratio test. So ratio test works very well when you have factorials and exponentials. So here we find the limit as n goes to infinity of an plus 1 over an. And once again, the absolute value bars are not necessary this time because I don't have any negativity going on. So n plus 1 will be 1 times 3 times 5, 2n minus 1, and then inputting n plus 1 will have 2n plus 1 minus 1 over 5 to the n plus 1, n plus 1 factorial, 5 to the n, n factorial, 1, 3, 5, up to 2n minus 1. Alright, so obviously in the numerator, these terms cancel with those terms, leaving us just 2n plus 1. Now this 5 to the n will cancel out with a 5 to the n from there, but leave a 5 behind. And then the n factorial over n plus 1 factorial will leave an n plus 1 in the denominator. So this limit is equal to 2/5, which is less than 1. So by the ratio test, this series converges absolutely. Next, we will find the radius of convergence and the interval of convergence for power series. So here we have the sum from 0 to infinity, x to the n over n factorial. We are going to apply the ratio test. So that will be x to the n plus 1 over n plus 1 factorial multiplied by n factorial over x to the n, which simplifies to the absolute value of x over n plus 1, which is equal to 0 no matter what x is. So since this limit is always 0, which is less than 1, this series converges for all x. Thus, the radius of convergence is infinite, and the interval of convergence, which I'm just going to call IOC for short, is negative infinity to infinity, meaning this series converges for all x's. Right, next we have root n times x to the n. So we'll find the limit as n goes to infinity of an plus 1 over an. So that will be root n plus 1 x to the n plus 1 over root n x to the n, which is the limit as n goes to infinity of the root n plus 1 over n absolute value of x. And this limit is 1 absolute value of x. So we have convergence if this is less than 1. This means that our radius of convergence is r equal to 1. And we have negative 1 is less than x, which is less than 1. So now we need to test x equals negative 1 and x equals positive 1 for convergence. So if we input x equals negative 1, I get the sum from n equals 0 to infinity, negative 1 to the n root n. And if I input x equals 1, I get the sum from 0 to infinity of just root n. And the first series diverges because if you try to apply the alternating series test, the limit of the terms does not go to 0. And the second one diverges by the test for divergence. So this is the interval of convergence. X is between negative 1 and 1. And next, let's find the interval of convergence and radius of convergence for a slightly more complicated series. So let's apply the ratio test. Negative 1 to the n plus 1, x minus 3 to the n plus 1, over, well, 2n plus 1 plus 1, multiplied by 2n plus 1 over negative 1 to the n, x minus 3 to the n. Alright, now those negative 1 to the n's don't matter because when you absolute value them you get 1, so they can just go away. Then we will have a singular x minus 3 absolute value left behind, and a 2n plus 1 over 2n plus 3. So this limit is the absolute value of x minus 3, and we will have convergence if this is less than 1. So my radius of convergence is still 1. And that implies that negative 1 is less than x minus 3, which is less than 1, or that 2 is less than x, which is less than 4. Now we just need to test 2 and 4 and see if we have convergence or divergence there. So when we have x equals 2, we get the sum from 0 to infinity, negative 1 to the n. Now 2 minus 3 is also negative 1 to the n over 2n plus 1, and that's the same thing as 1 over 2n plus 1. And this series diverges. You could show that using the limit comparison test. At x equals 3, we get the sum from 0 to infinity, negative 1 to the n over 2n plus 1, which converges by the AST. So the interval of convergence, oh, I didn't mean to say 3, I meant to say at x equals 4, sorry. The interval of convergence is 2 is less than x, which is less than or equal to 4, which you could also write as 2 to 4. Either one's fine. Next, we used geometric series to find power series representations for functions centered at various points. The most common thing was having functions centered at, or power series centered at 0. And so to do this, we're using the fact that the sum from n equals 0 to infinity, a r to the n is a over 1 minus r. So we have to make whatever we have look like a over 1 minus r. So f of x, that's the same thing as 8 over 4 times 1 plus x over 4, which is the same thing as 2 over 1 minus negative x over 4. And then I input 2 for a and negative x over 4 for r, and I have the sum from 0 to infinity, 2 negative x over 4 to the n, which is the same thing as the sum from 0 to infinity, negative 1 to the n, 2x to the n over 4 to the n, which you can actually simplify some more, but for now this is good enough. And its radius of convergence, we will have convergence if the absolute value of x over 4 is less than 1, which implies the absolute value of x is less than 4, and the radius of convergence is 4. Now you also could use integration or differentiation to find a power series for various types of functions. So what you have to notice here is that the derivative of ln x plus 2 is equal to 1 over x plus 2. So what you can do is find that series, and then if you integrate it, you get back ln x plus 2. Alright, so 1 over x plus 2 is the same thing as 1 over 2, 1 plus x over 2, which is the same thing as 1/2 over 1 minus negative x over 2, which is a sum from n equals 0 to infinity, 1/2 negative x over 2 to the n, or the sum from 0 to infinity, negative 1 to the n over 2 to the n plus 1 x to the n. So that's the sum for 1 over x plus 2. So therefore ln of x plus 2 is the integral of this sum So the negative 1 to the n over 2n plus 1 is just a constant. So what matters there is the integral of x to the n, which is x to the n plus 1 over n plus 1. So we have that ln of x plus 2 is represented by the sum from n equals 0 to infinity, negative 1 to the n over 2 to the n plus 1, x to the n plus 1 over n plus 1. And this series has the same radius of convergence as the original series, so we know that r is equal to 2. The interval of convergence, i.e. the convergence at the endpoints, may have changed. So what we notice here with 1 over 1 minus x to the second power is that the integral of 1 minus x to the negative second is 1 minus x to the negative first over negative 1 times another negative 1. So that's 1 over 1 minus x. So what that tells us is that the derivative of 1 over 1 minus x will equal 1 over 1 minus x, the quantity squared. So I will find a power series representation for 1 over 1 minus x, which is actually ridiculously easy. 1 over 1 minus x is the sum from 0 to infinity, x to the n. And then I will differentiate it. So the derivative of this series is the sum from n equals 1 to infinity, n x to the n minus 1. And that is equal to 1 over 1 minus x, the quantity squared. And the radius of convergence will be 1. Now, those power series depended upon the fact that you could manipulate what you had to somehow involve using the geometric sum formula. Now, here also we have Maclaurin series and Taylor series representations of functions, which you can find for any function within some specific boundaries, but generally speaking, for any function. So the definition of Maclaurin series was f of 0 plus f prime of 0 times x plus the second derivative at 0 over 2 factorial x squared plus the third derivative at 0 over 3 factorial x cubed, etc. So we're going to use that to find the Maclaurin series for f of x equals e to the x. Now notice that the nth derivative of e to the x is always equal to e to the x, no matter what. It's like the first derivative is e to the x, the second derivative is e to the x. So the nth derivative, fn of x, is equal to e to the x. So the nth derivative at 0 is e to the 0, which is 1. So this Maclaurin series will be 1 plus 1x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, etc., which can be expressed as the sum from 0 to infinity x to the n over n factorial. Now we can use this series that we found. We found that e to the x is equal to the sum from n equals 0 to infinity, x to the n over n factorial. We can use that to find the Maclaurin series for x to the 5th times e to the 3x squared. So we have x to the 5th times the sum from 0 to infinity, 3x squared to the n over n factorial, which is the same thing as x to the 5th times the sum from 0 to infinity, 3 to the n x to the 2n over n factorial. And bringing that x to the 5th in, its exponent adds to the exponent on the x to the 2n, over n factorial. Now, a Maclaurin series was just centered at x equals 0 or c equals 0. To approximate a function near a different value, we'll have to find a Taylor series. So if we wanted to estimate e to the 3x at values near 2, we will use a Taylor series centered at c equals 2. And the formula for a Taylor series is f of a plus f prime of a times x minus a plus f prime prime of a over 2 factorial x minus a squared. I just used a instead of c. Sorry. Now, to find this Taylor series, we have to have an expression for the nth derivative. And the first derivative is 3 e to the 3x. The second derivative is 3 squared e to the 3x. As you can see, the pattern is that the nth derivative will be 3 to the n e to the 3x. So my Maclaurin series, and inputting 2, we have that, first of all, f of 2 is e to the 6th. F prime of 2 is 3 e to the 6th times x minus 2. Then we will have 3 squared e to the 6th, x minus 2 squared over 2 factorial, etc., which is a sum from 0 to infinity. Now that e to the 6th is just a constant that shows everywhere, so I'm just going to put e to the 6th there. 3 to the n, x minus 2 to the n, all over n factorial.